good morning or good afternoon, again, whenever you're watching this. I'm going to go over the notes first, and then we're going to do some example problems. Then I will give you another problem set to work on. So today we're talking about current electricity. Now the formulas that you will need will be variations of these formulas. So they're not very hard, so they're basically just a few variables in each equation. The first one right here is power is equal to the current times the potential difference or the voltage. So P stands for power. This one is the potential difference or the voltage is equal to the current I times R, which is resistance. And when you're trying to find the energy, you multiply the power times the time over which it's occurring. Or if you look, this is IV, so this becomes IVT. Now, power is in watts or kilowatts. Current is measured in amperes. And resistance is measured in ohms. So we usually use an A here, we use the W here. So those are the formulas that you'll be using in their variations. Sometimes you'll have to find V for this one, so it'll be P over I. Sometimes you'll have to find R for this one, so it will be V over I. You just have to move them around. Okay, I'm going to be moving things around a little bit myself. The unit essential question for this chapter is, how are current, potential difference, and resistance related when involving energy transfer in circuits? We'll be talking more about circuits in the next chapter. Electrical energy can be converted into kinetic, sound, light, and all different types of thermal energies. Devices that convert motors, loudspeakers, lamps, heaters, air conditioners, they all convert electric energy into some other form of energy. Electric current is measured in amperes. We use the symbol I. I'm not sure why it's I. The rate, it is the rate of flow of electric charge. It's a coulomb per second is an ampere. We won't be doing much with batteries. We'll just talk about them a little bit. Batteries. There's several voltaic or galvanic cells that convert chemical energy into electric energy. Photovoltaic cells convert light energy into electric energy. A lot of the old calculators used that, had that type of a battery cell. Electric circuit is a closed loop in which electrons flow consisting of an electric pump that increases the potential energy of electrons connected to a device that reduces the potential energy of electrons. So anything that is using electricity is in a circuit. We'll talk more about that in the next chapter. I know you OCD people, I'm probably driving you crazy. Resistance. Resistance occurs when a device reduces the potential of electrons flowing through it. The drop of potential energy of electrons in a motor creates kinetic energy. The net change in potential around a circuit is zero. The current is the same everywhere in a circuit. Once again, when we start doing circuits, you'll understand this better. Some of you have already done it in Mr. McNeil's classes. The property that determines how much current will flow, R is equal to V over I, and it's measured in ohms. And it's basically from a scientist named Ohm. He has Ohm's law. Now, what I want to talk to you about resistance is anything that produces heat has resistance. For example, the best viewing source of a resistor is if you went to your toaster. What's happening in your toaster is the resistance is big in the wires that are going across your toaster, which causes them to heat up and actually become red. That is an indicator that the electricity is, that the flow of electrons is being resisted, and it allows it to heat up. Other good examples of devices that have high resistance would be curling irons, blow dryers. They use a lot of energy, and they have a great deal of resistance. Okay, moving along. An ammeter. It's a specific device that measures current. It would be placed, I believe in series, to find out how much current is going across the circuit. Resistor is a device that's designed to have a specific, you only need one P there, by the way, resistance. They're usually long, thin wires made of graphite or a semiconductor. Superconductors are materials that have zero resistance. There isn't a potential drop across it. Current flows out of the positive terminal towards the negative terminal of a battery. When we start doing schematics, you'll be able to see that more clearly. Conventional current arrows are drawn in the direction that the positive carriers would go. They from positive to negative, just like the diagrams we had with the electric fields. Ammeters and voltmeters are connected in circuits to measure current and potential difference. Okay, rates of change. Here's those formulas. And there's a couple on here that I didn't have in the very beginning. P is equal to IV, P is equal to E over T. P is equal to I squared R, P is equal to V squared R. A kilowatt hour is 1,000 watts that are delivered continuously for 3,600 seconds, which is an hour. So a kilowatt hour has 3.6 times 10 to the 6, 3.6 million joules. Okay, here we go with Ohm's law. Ohm's law states that current is directly proportional to the potential difference. So it's directly proportional, but it's inversely proportional to the current. How does a human body act as a variable resistor? Well, when the skin is dry, its resistance is high enough to keep currents that are produced by small, moderate voltages low. Once the skin is wet, its resistance is lower, and the electric current can rise to dangerous levels. So that's why you don't want to put your toaster in the bathwater with you. Just kidding. Please don't ever do that. Please don't ever, ever, ever do that. You will die. Don't do that. Once again, don't put your toaster in the bathtub with you. Thermal energy. E is equal to PT. E is equal to I squared RT. Some more formulas. E is equal to V squared over R times T. They're all just rearrangements of different formulas. If the power is dissipated at a uniform rate, the thermal energy converted equals power multiplied by time. Unwanted thermal energy produced in the transmission of electric energy is called Joule heating loss. So anything that we produce that we can't use, it's called a Joule heating loss, and it's equal to I squared R. In order to minimize this loss, the current in the transmission lines needs to be low. Transmitting at higher voltages enables current to be reduced without reducing the power. So that's how that happens with the power lines. All right, so now what we're going to do is we're going to do some example problems. You're going to find out that these are fairly easy. They're not bad at all. Now I have to try and fix this again. My copier, when I send it from my phone, it does weird things to it. So it makes it look a lot smaller. I don't know if you'll be able to see it, but you'll have it downloaded if you did that. I'm going to get rid of my Honors Algebra 2 and start off. The current through a light bulb connected across a terminal of 125 volt. Write that down right away. V is equal to 125. That should be a no-brainer because V is V. The current is 0.05 amperes. 0.05 amperes. At what rate does the bulb convert electric energy to light? So basically what I'm asking you is, what is the power? Power is equal to IV. And I meant to make that 0.5 instead of 0.05, but when we go ahead and do that way, 0.05 times 125 should be 6.3 watts. If I'm wrong on any of these, guys, just correct it. You know how I make mistakes every once in a while. I'm human. Number 2. A car battery causes a current of 2.0 amperes through a lamp and produces a 12 volts across it. What is the power used by the lamp? Again, this is just P is equal to IV. Just multiply them together. I is 2. Don't even need a calculator for this one. It's 24. And the unit is watts for power. Number 3. What is the current through a 75, that's what we're looking for, 75 watt, that's the power, that is connected to a 125 volt source? Well, we want I now, so I'm just going to divide by V. I is equal to P over V. 75 divided by 125. Now, it's hard for you to see how these units would change. It's hard to do a unit dimension analysis of this. You just kind of have to know that I is measured in amps. And that's 0.6. And should we have 2? Yes, we should. Sig figs. Number 4. The current through the starter motor of a car is 210 amps. If the battery maintains 12 volts across the motor, how much electric energy is delivered to the starter in 10 seconds? Looking for energy. And if you recall from first set of formulas that I gave you, it's IVT. They all three get multiplied together. 210 times 12 times 10. And that is going to be 25,200 using sig figs 2.5 times 10 to the 4th. And what is a unit for energy? I'll give you a second here. Let's try and remember. Wish I could call on somebody. Joules. That is correct. Number 5. Now we have some resistance in here. An automobile panel lamp with a resistance, and you'll notice that sometimes the resistance, if you have a resistance, is going to produce heat. That's why most light bulbs are hot to touch, and that's what's going to be happening here. An automobile panel lamp with a resistance of 33 ohms is placed across a 12-volt battery. What is the current through the circuit? I equals question mark. Okay, if you look back at your formulas that I gave you at the very beginning, I gave you V is equal to IR. And that's one that I always remembered, because back in the day when I was in high school and we had to keep these memorized, the IR was a big plant, so I always kept the I and the R together. Ingersoll Rand, by the way. So I'm looking for I. I is equal to V over R. And we have all of those things. So these are relatively simple problems. Once you figure out what is what, you just plug it. And it's like my college professor used to call these plug and chug problems. You plug the numbers in, you chug an answer out. That ends up being 0.36 amps. Number 6. A sensor uses 2.0 times 10 to the negative 4th amperes. I is equal to 2 times 10 to the negative 4th amperes of current when it is operated by a 3-volt battery. That's my voltage or my potential difference. What is a resistance? Okay, now when I'm solving for R, if I look back up here, I have to divide both sides by I. So R is equal to V over I. 3.0 divided by 2.0 times 10 to the negative 4th. And that is going to be 1.5 times 10 to the positive 4th. And that is ohms. That's a very high resistance. Number 7. A 75 watt, that's a power, is connected to 125 volts. What is the current through the lamp? I have P and V. So if you look back up here, I actually have this one solved already for I. I is equal to P over V. (75) divided by 125, and we've seen those numbers before. 0.660 amperes. The B, what is the resistance? Okay, R is equal to, we have V and we have I. R is equal to V over I. We just found I. Hopefully it's right. If it's wrong, we've made a mistake. This is 125 twice. We made a mistake. Divided by 0.6. And there are other formulas that you can use to find this. If you looked at all of those formulas that we had in the PowerPoint, there are a lot of different formulas that you could actually end up using. And this one is 208 ohms. If we stay true to sig figs, we would call that 2.1 times 10 to the second ohms. Number 18. Okay, I'm going to bring this like this because this is what my printer did. Okay, a 15 ohm, so that's R, heater operates on 120 volts. What is the current through the heater? Well, we are looking for I. We come back up to this top one, we see it's V over I is V over R. So it is going to be 120 divided by 15, which is a nice number, 8. And I am writing off the paper. You guys are probably screaming, you're not writing on the paper. There you go. And then the B part. I'm going to put the B part underneath here so you can see it. B. How much energy is used by the heater in 30 seconds? Energy is equal to, well, we can use IVT. There are other formulas we certainly could use. So this will be 8 times 120 times 30. Which is 2.88 times 10 to the 4th energy measured in joules. Okay, now the last question's an interesting question. I'm going to move that out of the way and move this up. We have an electric space heater, and it's interesting to find out how much it would actually cost to run this. If you had a space heater, how much is it costing you a month to run if you run it for 5 hours a day? So it draws 15 amps, that's the current. Voltage is 120. It is operated on the average for 5 hours a day. How much power does the heater use? So A, P is equal to IV. That is going to be 15 times 120. And that's 1800 watts. B, how much energy in kilowatt hours does it consume in 30 days? Okay, first of all, we're looking for how much energy in kilowatt hours. So we have 1800 watts. Let's change that to kilowatts. 1.8 kilowatts. I was going to put times 10 to the third, but we are converting it, so it's 1.8 kilowatts. And then hours. So they want to know when we multiply these out, how many hours in 30 days. So this is going to be 1.8, 5 hours every day for 30 days. So 270 kilowatt hours. Kilowatt hours. So what I did, guys, was I converted this to kilowatt hours. There were 30 days, they used it for 5 hours. So 30 times 5, so this is kilowatt, and this is hours. This is a total hours. Now see, I typed this up, and when the book had, sorry guys, the book had 12 cents per kilowatt hour, and it's an old book, so I thought, well, I'll just double it when I typed this up. And then I thought, well, let me look this up. And I found a couple interesting facts when I looked it up. I want you to think for a second, which state do you think has the highest cost in cents for every kilowatt hour? How many cents per kilowatt hour do you think, which state has the highest? And I'll tell you, it's 22 cents per kilowatt hour. It is Alaska. Alaska has the highest rate of electricity, which makes sense. And the lowest, which I never would have guessed, is Louisiana with 9.4 cents. And here we are, Pennsylvania, a little bit more than 14 cents. So we're going to change this up to 14 cents. It didn't double like I thought it would. So we want to know, at 14 cents per kilowatt hour, how much does it cost to operate the heater for 30 days? Well, we know we've got 270 kilowatts, and I'm just going to put the cost is equal to 270 kilowatt hours, and it's 14 cents, or I'll put dollars there, per kilowatt hour. So the kilowatt hours would cancel, and 270 times 14 cents would be $37.80 to run an electric heater 5 hours for a day for 30 days. I don't know if you think that it should have been higher or lower, what your thought process would have been on that. All right, so I am going to upload a problem set for you. I think that this is probably enough for today for you to have to deal with. So tomorrow on Wednesday, I will be uploading a problem set that I will ask you to have done by the end of the day Friday. I hope you guys are all doing well. Once again, I can't say it enough how much I miss you. You all take care.